So now we're in section 11.2. The formal title is Inference about Two Means Dependent Samples. We'll talk about the details in a moment. So what you have to pay attention to, and this is very important, we're working with two populations just like we were in 11.1, but now, very different, we're working with means, not proportions. So we'll be dealing with mu's and x bars, etc. But the similarity between the last section, 11.1, is that we're still working with two populations, but now we're not working with proportions, we're working with means, and now we're working with a very special case, dependent samples, matched pairs. In 11.3, in the next lecture, we'll be working with two populations still. We'll still be working with means, but we'll look at independent samples in 11.3, but now in 11.2, we're working with these matched pairs dependent samples. We have two objectives. We need to do hypothesis tests with matched pairs, and we have to do confidence intervals with matched pairs. Hypothesis tests with matched pairs and confidence intervals for matched pairs. It's going to be relatively easy. The notation's a little bit ugly, all right? I've tried to clean it up and make it look presentable, but most of this will be done on StatCrunch, so you shouldn't become too concerned. So statistical inference methods on matched pairs data use the same methods as inference on a single population mean. Even though you have two populations that you're going to see in a moment, that the two populations collapse into one population of something called differences. When we're working with one population and means, what we're dealing with is the information that we found in section 8.1, 9.2, and 10.3. 8.1, 9.2, and 10.3. You can pause this and read this, but the main thing here is that when you're working with this situation, these matched pair situations, it's going to work a lot like sections 9.2 and 10.3, meaning you either need a large sample size, greater or equal to 30, or if your sample size is less than 30, you have to make sure that the parent population is normally distributed and that you have no outliers in the sample. All right. You see where it says the differences are normally distributed, no outliers? That means no outliers in the sample, and the parent population, which is going to be denoted by D subscript I, that has to be assumed to be normal. We'll talk about more of that in a moment. So this is a really important slide, and there's going to be a lot of information here, a lot of symbolic information, and I'm going to go over it carefully with you so that you understand. Whenever you're doing this matched pair situation, you're always dealing with four populations, and let's examine that. You have the first population that we're going to label X subscripted I. All right, so then we're going to have a second population, and all the data values in that are going to be Y subscript I's. Then, this is your third population now in the center where my cursor is. We're going to analyze the differences between the two populations. Okay, you see here where we're going to look at the differences. The differences are analyzed. That's important. Okay, so what we're going to have are these D subscripted I's, the D subscripted I's that result from doing a subtraction. Remember, these are matched pairs. Now, suppose, okay, I have one person taking a medicine A, and then I look at the level of pain they have after that, and then they take medicine B. I compare those two numbers. The X's would be their pain level after medicine A. The Y's would be their pain level after medicine B, and I'm interested in the difference between those two results. Or another example we were looking at later in the section is we want to compare the heights of sons to fathers. So let's specify a specific son, like the firstborn son. The X's would be the heights of the firstborn sons, and then the matched pairs would be the heights of their fathers. Okay, and I'm trying to analyze the difference in those heights, whether sons are taller or fathers are taller or they're about the same, but I'm trying to analyze the difference between those two population values. Okay, so first population of X's, a second population of Y's, but we're assuming we have matched pairs that the X's and Y's all go together. So I can subtract father, son, etc. Okay. Then this is our parent population. This DI, D subscript I, this is our parent population now. Think back to section 8.1. We start taking samples. We take every sample possible of size n, and from each one of those samples we extract a D bar, which would be a sample mean. Take first sample mean, second sample mean. Then I have a whole new population of D bars, just like we had a whole new population of X bars. But this fourth population of the D bars, and this is the central limit theorem, sample means, this is theoretical and hypothetical. We're never going to do this over and over again. We just want to know what would be the long-term pattern for all possible D bar sample means. If we just take one out of the sample, we want to know how often that's going to provide valuable information about this mu subscripted D. What is mu subscripted D? It's the average difference if we look at the entire two populations subtracted. So I look at all possible differences between, say, for example, fathers and sons. The average difference is going to be mu for this population here. We take one D bar and we use that to estimate mu subscripted D, just like we used X bar to estimate mu. Okay. This fourth population is theoretical, and we use that to understand what the long-term pattern is and how often a single D bar will be an accurate measure of mu subscript D. Okay. This distribution over here, this theoretical distribution, has a normal distribution if the conditions are met, and its mean is mu D bar, mu subscript D bar. Just like before, mu equaled mu of X bar, mu of D bar equals mu of all the D's. We're going to just use, redundantly, we're going to use one of these coming out of the sample of this population here to estimate mu. Now, we know what the X's subscript I's are. Those are the individual data values in the first population. We know what the Y's are, individual data values in the second population. They're assumed to be matched pairs. And so we can look at the difference between all those values, x1 minus y1, x2 minus y2, etc. I have a whole new population. This is my parent population. This is my parent population here. Okay. And then I construct a fourth hypothetically to understand what the long-term pattern is for all possible sample means coming out of this third population. So the null hypothesis is always that the mean of this overall population of differences is 0. Where is this mu subscript D coming from? It's coming from this third population. All right. It's the overall average value of all these differences. So here, mu subscript D is assumed to be 0, 0, 0 all the way across, and then you have 3 ways of setting up the alternative. Alpha we know is the level of significance. We've talked about choosing alpha and how that's always provided in textbook situations. In order to compute the p-value, you actually have to compute something called a test statistic. If you want the details about this, this is a reduced formula. It's just a modification of the formula for computing z-scores, telling you how many standard deviations you are above the mean or below the mean. Okay. Don't worry about this too much. Okay. Degree of freedom is still n minus 1. But we're going to do this primarily using technology. Draw a diagram, two-tailed test, left-tailed test, right-tailed test, like before. Again, this test statistic, it's valid. It's an important detail if you want it to be an important detail, but because we're using StatCrunch to compute these values, it won't be that big of a deal. What it tells us is how many standard deviations our sample value was above or below the mean. On StatCrunch, you go to T-stats paired. This is very special, all right? You tell it where your X values are. You tell it where the Y values are. Okay. You click Save Differences right here. That's important. Click Save Differences. Set up your null and alternative hypotheses. This will always be 0, right? And there's 3 ways to do this. And then do compute. Now let's go back to the saving differences. When you save differences and hit compute, it'll automatically fill this in right here. Sometimes for the homework you need these differences because they want the mean or the standard deviation of these differences. All right. And in order to get the mean and standard deviation of these differences, you would just go to Stat, Summary Stats, Columns like you did in Chapter 3 and choose mean and standard deviation. Okay. Here's your p-value. Here's your test statistic. As always, if the p-value is less than or equal to alpha, reject the null. If it's greater, fail to reject. Then state the conclusion in the context of the question. We talked about what robust means. Remember, when you have a small sample size, you have to require that the parent population is normally distributed. Robust in this sense just means that you can have minor departures away from that. So you just need approximate normality of the parent population. So here's an example. Remember we were talking about hotels in 11.1. They've changed the name of the hotel chains, but it's the same story. We want to compare the overall price difference between Hampton Inn hotels and La Quinta Inn hotels. The population of X's would be the population of all prices for the Hampton Inn. The population of the Y's would be the prices of all the La Quinta Inn hotel prices. Okay. Then we pair them up. Each city, like San Francisco, Los Angeles, Seattle, Chicago, we pair them up and we subtract the difference in price. We want to estimate the overall difference in price between those two hotel chains. In order to do that, we just take a sample of 10 values from 10 cities, all right? And we're going to test the claim that they're priced differently. That's going to give us a two-tailed test, and they give us the level of significance at 5%. So these are our samples from these 10 cities. Now, where did those differences come from? Those are the D subscript I's. Where did those come from? By subtracting these numbers down through these 10 cities. These are D subscript I's. What is D bar? D bar is the average difference for this. And we're going to use that average difference in the sample, the mean difference in the sample, to estimate what's going on with the population of all possible differences. Again, where did this S subscript D come from? It's the standard deviation of these 10 numbers. Because we have only 10 values, all right, 10 little D subscript I's in our sample, we have a small sample, we have to do a normal probability plot on those numbers, and that's what this is. That's fine. And we have to do a box plot to make sure there's no outliers in the sample. So we set up the null and alternative hypotheses, right? The conditions have already been met and tested. The level of significance has been given, right? We compute the p-value using technology, and the p-value is very small. It's 0.0005. Notice it's much less than the 0.05 alpha. Since the p-value is less than the level of significance, we reject the null hypothesis. Okay, remember null. There is sufficient evidence, because we're rejecting the null, there's sufficient evidence to conclude that the Hampton Inn hotels and La Quinta hotels are priced differently at the alpha equals 5% level of significance. That's it. Now this is a problem in the homework, and the only reason I'm going to show you this is that you have to make sure that you identify, there's only 4 or 5 of these homework problems, you identify which way the homework wants the subtraction done. Look right here. DI wants the YI minus the XI. Whatever you do, understand that they want sample 1 to be the Y's, sample 2 to be the X's. You have to pay attention to that. See the reversal of variables. In the sample 1, you put the sons. In sample 2, you put the fathers. Let's go back. See how fathers looks like it would be the first and sons looks like it would be the second, but they're telling us no. They want the sons first and the fathers second. Pay attention to those types of details. Construct and interpret confidence intervals. What we're trying to do is estimate the overall population difference. The overall population difference. This is a mu. This is a population mean. We're trying to estimate the population mean for that. We're trying to estimate the population mean for this population, mu subscript d. And we're going to do that by taking 1 d bar as our point estimate and using that to estimate mu subscript d. So mu subscript d equals the point estimate d bar plus or minus this t sub alpha over 2 and then this S subscript D over the square root of n. What this is, this T sub alpha over 2, this tells me how many standard deviations wide the margin of error needs to be to match a given confidence level. Look what I'm talking about. This multiplication, T sub alpha over 2 times this other expression here on the right, that's the margin of error. Point estimate minus the margin of error, point estimate plus the margin of error. Then this right here is an approximation to the standard deviation for the population of all differences. This expression right here is an approximation to the standard deviation for the population of all the differences. This is the mean for the population of all the differences. This is an approximation to the standard deviation. It would be denoted, I don't have it here, as sigma subscript d. Sigma subscript d. Construct a 90% confidence interval, right? So we already know that d bar is 51.4 from before. We know that the standard deviation S subscript d is 30.8336, and so we get 51.4 point estimate plus or minus 1.833. This is T sub alpha over 2 S divided by the square root of n. Where did this number come from? If I really wanted that number, you know, if I needed it in the homework or I needed to compute it, I would just go to the StatCrunch, the T calculator, right, and tell it that I want between, right, and I want the between in this case to be 90%, and it would give me this value right here, the 1.833. So that means that we're 90% confident that the mean difference in hotel room price between Ramada Inn versus La Quinta Inn is between $33.53 and $69.27.